Hello everybody and welcome back to another episode of this series. We are still working on APIC initialization, and today we are going to start working on interrupts. So let's get started. Right, so last time we were working on this, so we've created a first initialization of the APIC subsystem here. So I made some changes. I moved the constants we've created to this enum here, registers. I've also created this function here, read register, that takes an offset, or maybe I should call it register from registers as that to APIC base, and basically gets the value from there. So that is fine. I also went ahead and did something else. So if I can go here to SMP, so I've added the missing callbacks here to our notification context. And that is to be able to get some important data that we are going to need later on. So especially this one here, the local APIC NMI. And I think I should probably open the ACPI documentation page here, just so that we can follow along. So ACPI spec. Right, and if I remember correctly, that's under chapter 5, tables. And if we go over here, and maybe I should look up NMI. Yeah, sure. So, local APIC NMI. So basically what this tells us is that for every local interrupt, so n, for which we have 2, we have 0 and 1. So those were, I guess we could have seen those over here. Chapter 12, local APIC handling interrupts. There we go. So we have 2 pins, local interrupt 0 and local interrupt 1 that we can work with. And this table here, supposedly, is going to tell us, so for each processor UID, for this local interrupt number, we need to set an NMI interrupt with the given flags. Is how I interpret this. And here, just reading this, a value of 255 basically signifies that this applies to all processors. So when starting up and setting up the ACPI stuff, or rather the local APIC stuff, each CPU should read the data that we get from this local APIC NMI, and they should try and match their CPU ID and set those values. And of course, if they see 0xFF, they should also set those values. And there's another thing to keep in mind here, is that for X2 APIC, we have an equivalent structure here that basically gives us the same info. The only thing that changes is that the processor ID is now 4 bytes instead of 1 byte. So that's the main change here. So yeah, okay, so here we have 2 problems. We have, we need to know what is the ID for our current processor, our current CPU, and we need to know how to interpret these flags here to well, basically to set up the local API interrupts. So first of all, let's build this and run it. So cool, we don't have any info here. Right, so let me do local, let's call it NMI here, and here we can go ahead and do log.debug, where it's something like, yeah, sure. And this here can become NMI. Sure. Okay, let's see here. So in our case here, we have just a single entry that has processor UID to 55, so that's all processors, and it wants to be set for local interrupt 1, so that's lint 1. And I think I forgot to include the flags. So I guess that would be in ACPI. Yeah. So how about I just debug this here? So NMI be any, and then we just so local APIC NMI. That's fine. All right, let's rebuild this. Just want to see what we have, what info we have there. Right. So here we do have polarity is bus conforming, whatever that means. Trigger mode also reserved, we don't care. So yeah, so we just need polarity and trigger mode, and those are both bus conforming. So now the question now is, what does bus conforming mean in this case? Well, I know what bus conforming means, but what does it translate to? So if we go back here, bus conforming means that it conforms to the specifications of the bus. But what are the specifications in our case? That's the actual question. Okay. Right. So here we have 3 problems then to answer. First is, how do we get the CPU ID so that we know which CPU we are, and basically be able to load the equivalent or the matching local APIC NMIs. Second is, how do we actually get those? Because here we, the way the code is structured now is that this SMP module here creates this iteration context, and then we ask the ACPI subsystem to give us all the info it has about a certain table. And it basically notifies us back on that context. That also means that now from that context, we need to store the needed data that we need to call other subsystems with. And here we do have a bit of an issue, because this is the SMP submodule, whereas if I go back to main, we initialize the SMP submodule, and then we initialize the core just after that. So probably the thing I'm talking about would need to be done in the core itself. So probably this here would migrate to CPU. Yeah, that might be a better idea than what we did here. So enable, or should I call it init local APIC. Does that sound okay? I guess it does. So here we don't really need this, but now we do need these things here that we have stored. So first let's get memory. So that's that. And now we just need to get the base address from SMP. Now, how do we go about this without this becoming absolute trash? So these here we can set to public if we wish to. So that can become public. This here I don't really care about for now. I'm not even sure why we needed that. Yeah. And we probably need to structure these things a bit more, I think. So this here would be local APIC. This here would be IO APIC. And this here would be whatever. Don't really care, so let's put it with local APIC. Right, so now we need to also store the NMI. So we need some sort of map that has, so let's think about this. We know how many CPUs we want to have. But I'm not sure if we can have one mapping per CPU or if we can have any number of mappings per CPU. So that's what I'm going to try to find out from this here. So that means that here to store the local APIC AMI, I might actually go for some sort of map. I'm just thinking here. Or we can have that be an array. Yeah, we can probably have that be an array. Whereas, yeah, okay, so that might be a good idea actually. So we, yeah, okay, hold on. So pub var, let's call this local APIC NMI. This here would be an array of, so we already know, or we should know how many possible CPUs we have. So that's in, do we already have options? No. Options, there we go. So here we should go for options.max CPU plus 1, right? Because we need to make space for the 0xFF case. And we need to, so here we've encoded the CPU ID. So what we need now is to get the local interrupt ID and the flags, basically. Yeah, okay. So that means that we need to create this new format, I guess. Do we actually need to create a new format? Yeah, I think we do. Or we can just store this one here. Local NMI found event. So where is that? That should be under ACPI events. Yeah. So local animi found events, but this one here still has flags. All right, I think we can do this. So we can actually just create flags. So here, both of these need flags, and I think they need the same type of flags. So so interrupt flags is a struct that has so polarity. So this needs to be an enum of yeah, we'll check. And so polarity and trigger mode, I think. Okay. So this one here, trigger mode. Mode, so this also need to be an enum. So polarity needs to be 0, 1, or 3. So hold on, I forgot. So conforming plus conforming is 0. Active high is 1. And actually I forget. These don't need that. And active low is 3. And of course here we need to tell it that this is U8 backed. Actually, we don't really need these, do we? So that means that we don't need this. Right, so trigger modes. Trigger modes, we want bus conforming, edge, and level triggered. So bus conforming all over the place. Edge triggered and level triggered. Triggered. Yeah. Okay. Cool. So here probably pub function from ACPI. That would take sure, ACPI flags. Let's just call it flags. Fine. ACPI flags. And this would be what would this be? I'm not sure. So we'll skip that. So here would be interrupt flags. And so does this one here. Interrupt flags. Cool. Okay, so I guess now we do have a problem in ACPI. So here we need flags. And here also I think we need flags, yeah. Cool. Now how do we go about this? We need to public function make flags from ACPI. Sure. ACPI flags. This one here would be ACPI types dot table signatures. No. MADT and MPS int flags. Cool. And this should return ACPI events dot interrupt flags. Okay. So let's call this const polarity is we'll switch on ACPI flags dot polarity. So we get no completion here, huh? Yeah, so there's dot polarity, and we check for these. Hold on a minute. I can do this faster. So this one here would need to become bus conforming. Right, this one here would be active high also. This one here we don't care, and this one here would be active low. And of course, if we get that other case, it's unreachable, I think. Whoops. There we go. And of course, this one here, we already know what type it is, or what type it should be. So this one here would be ACPI events dot interrupt flags dot polarity. And of course, we go here and we get this to here. We call it const polarity is, and of course, we make that public. This one here becomes that one. This one here becomes pump const trigger mode. And of course, we do this, and then trigger mode. Everybody happy? Think so. Wait. Oh, a CPI. Okay, of course. Right. So next comes here. Trigger mode is, of course, this is ACPI events dot interrupt flags dot trigger mode. Of course, this one here is switch on ACPI flags dot trigger mode. Of course. Hopefully we get help here. Yes, we do. So this one here becomes bus conforming. No challenge there. Edge triggered is also edge triggered, and level triggered becomes pretty much the same. Level triggered. This one here is unreachable. Reachable, if I can type it. Fine. Cool. So here we return a new thing with polarity. Polarity is polarity, and trigger mode mond is trigger mode. There we go. And now we can go up here somewhere. Right, so this one here becomes make flags from whatever that is, and this becomes interrupt, or rather end source override dot flags. Oops. Are we happy about that? I think we are. So this one here also becomes flags from ACPI. Local APIC animi dot flags. Whoops. Okay, so let's just give this a quick build, see where we okay, so undeclared identifier, that's fine. Expected expression found Bob, that's also fine. So let's fix those first. So this guy here. We said that we'd like this to be ACPI events, local APIC, whatever found event. Sure. And of course, we need to initialize this or something. So just going to set it to undefined for now. Right. So here I'm also going to go ahead and do local APIC inimi of, so inimi, okay, so let's do const index is inimi.processor ID, that's a U8, and I want to actually wrap add. Is that how we go? That's how we go, I think. 1 to that. And this would be index. So basically what this does is 0xff will go to 0, and then every other ID from there would basically get bumped up. So here, fix me, we need to bounce check this to avoid problems with CPU IDs larger than possible CPUs. There we go. So this one here is inimi. Think that would be pretty okay. Right. Actually, I think the bounce check should be fairly easy. Why am I? Yeah. So if inimi inimi.processor UID is larger or equal to options.max CPU, return. There we go. Done. Right, so we now need to go to CPU and fix whatever this is here. So this is smp dot that dot seg, of course. All right. Let's see how that goes. Oh yeah, of course. This is not an oxide language. So this here becomes else. There we go. Okay. Am I missing something? I am missing something. So wait, hold on a minute. Okay, first of all, let's do some cleanup. ACPI. Not this. This one, I think. And if we go up here, we can just probably remove this. It's kind of useless now. And I want to go to CPU here. And of course, we never called init local APIC, so that's what I was missing. Cool. All right, so some more problems here. Expected void found. Yeah, of course. This here needs to become errorable. So try. Okay, so we still get the XAPIC enabled, that's fine. Everything else works okay. All right, so now that's for initializing the local APIC. Actually, I'm not going to call this init, I'm going to call this enable. Because basically at the end of the day, that's what we are doing here, just enabling this. So now what I want to do is I I want to set, so how do we go about this? Let's call this public function init interrupt. How do we call this thing? Local interrupts. Yeah, sure. Does this ever fail? Not sure. Okay, so this one here needs to take. We need to get some things. We need to get. Okay. So probably we need to go ahead and do. Set up. Yeah, I'm not sure about this. Yeah, so hold on, let's just leave it at that. And here we need to take local minimize. Sure. And this here is that array we've created before. Except that here I'm just going to take a sort of slice of a struct that I'm just going to create ad hoc here. So this struct here will have. So we already know that all of these items that we are going to take are destined for our own CPU. So we only need to take the local interrupt, so lint number, that should be a U8. And we need to also take flags. Now that's, so flags, that's ACPI event. Maybe I should just create another struct here for flags. Just to, yeah, we'll see about this. So polarity is, so how do we expect this, or how does this thing here expect to get those? So there's a table here. So these 3 bits here would need to be NMI. That's fine. Here, input, or rather interrupt input pin polarity here goes here. And then here we have trigger mode, edge or level goes into this bit here. And of course we have a mask to enable or disable the interrupts. What does the mask go? The mask is bit 17, except for the timer where it's bit 16. Am I reading that right? Maybe. Yeah, okay. Right, so we also need this mask thing here. Right, so I'm probably making this more complicated than it needs to be. Yeah, and I think that this just shows that I hadn't thought about this enough. But we move. Right, so here what I want to do is ACPI events local NMI event found. So I probably would like to have, so where does this live? This lives in our shared library, so that's fine, I think. Where where does this live? This lives in architecture, so I think we can import that. So const Falcon is import Falcon, and const ACPI events is falcon.acpi events. Can I? Yep. All right. So that means that now this whole thing here we can change to just be ACPI events dot local this. Very nice. And of course here we need to set up all the interrupts. So we need to set up all of these things here. So but I think since we still aren't using any of those, so thermal sensor, not gonna use that. Yeah, not on my bucket list. Error maybe, that might be an option. Corrected machine check errors or whatever. I'm just gonna successfully ignore that, I think. Which leaves us with local interrupt 0 and 1, error, maybe in the future, performance monitor counters, if we start using the performance monitors, so that we can actually report some stats on how well we are executing stuff. So branch misses, predictions and stuff like that, TLB and cache hits or misses. So that's should go there. Those things go there. But for now, let's just focus on these two here. The other ones I'm just going to mask off. So I'm just going to set mask to 1. And mask to 1 means that, so here we have 16 bits and mask is the 17th bit. So I'm just going to create this here, const interrupt mask, and this would be, so we have 16 bits and the mask is the 17th bit. And of course we want this whole thing to be 32 bits, so that's a U32 right there. Cool. So now we just need to know how to actually write to these addresses, and I think we just need to create write register, not a function here that would call write register, takes a register from registers and a value, U32, returns void. And we do pretty much the same thing, except that here this doesn't return anything, and we just set to val. Cool. Right, so let's go one by one. So write register so correct machine check interrupt is to F0. Is that to F0? Yep. All right. So that's the correct one, and the value would be int mask. Okay. Let's go for the next one. Register. So I'm just going to leave the interrupts to the end. So error status no. LVT error to 370. 370. Yep. Okay. And that's int mask. So we need 2 more of those. So this one here is LVT performance monitoring, so 340, yep. And then this one here is LVT thermal sensor 330. Is that it? Yep. Okay, cool. All of these look pretty good now. Const Right, so we actually get an array or slice of local APIC NMIs. That means that we need to go for NMI, or rather for local APIC NMI, we capture NMI. And for each NMI, we need to, we actually need a const CPU ID, which we need to get somehow. So this would be CPU dot ID. Except that here we are actually sure that should work still. CPU.sig, maybe CPU.sig. Wow. CPU.sig, right. So this is something we need to work on. Actually, I'm just going to go ahead so that I don't forget this. So hold on a minute. These are all things we want to have. So now, so thinking, public function ID returns a U32, I guess. You could have made this EU8. Not really thinking about supporting more than 255 CPUs at once. But we have, we want to support X2 APIC, so yeah, let's leave it be. U32, and that means that there's also another thing we need to remember is that we have this CPU data here that basically has these things. Oh, I actually have a CPU ID type, so that's fairly handy. Cool. So here we have the APIC ID, which would also be the CPU ID. Except that this CPU data here, or rather the actual CPU data in the main CPU here, there we go. So this is what we want to have, to get, rather. So this CPU data here needs to be pointed to by GS. And this is something we haven't done yet. So something we need to do fairly soon. But that means that when we, or rather, when we want to read from this, so we want to read the ID, we are going to do some fairly bizarre things where we are going to actually do some volatile ASM, and here just hit this with move so GS 0 to some sort of value here. Let's call it ID, and of course this needs to, so we have outputs, so ID is, how do we go about this? Something like register, and then we send that as a CPU ID. And of course here we return is that how we go about this? think it is. Right, so now if we go back here, fine. So now this one here, if NMI, dot processor UID is different from our current CPU ID, or NMI dot processor UID is there should be an AND is different from 0xFF, then we just basically skip this item here. Otherwise, we want to actually write register so const value is equal to 0 for now. I'm just going to set value here to be U32. And so I'm just thinking here. So we need to do a few things first. Let's go over to this. We need to know if we are using int0 or int1. So that's the first thing to decide. So register is if NMI dot lint number is 0, should we probably do something like this? So 0 goes to, so let's just do this is registers. So this one is LVT lint 0, 1 goes to LVT lint 1. Unreachable. I think that would be good. So here we'd need registers and of course value. Right, so now that we know which register we want to write to, we need to decide which values we want to write. So here masked will be 0, so we don't need to write that. Things we need to write is remote IRR is read only, I think, from what I've seen earlier. Yep. So the only things we need to write are input type, pin polarity, and trigger mode. So I'm just going to go back to read this in a bit, but we also need to write the delivery mode, and so NMI is 100. This is in binary, and the vector information is ignored. So vector would just be zeros, I guess, since no one cares. Now let's go ahead and read this. So trigger mode for int0 and int1, 0 is, or rather 0 value is edge sensitive, 1 is level. This flag is only used when the delivery mode is fixed. Okay, so no one cares if we are not fixed. NMI or int, the trigger mode is always edge sensitive. When timer and error interrupts are always treated as that. Okay, so that we don't care about. Software should always set trigger mode in LVT1 register to 0, edge sensitive. Okay. So, hold on a minute. So when the delivery mode is NMI, it's edge sensitive always. When the delivery mode is okay, and local interrupt 1 is always edge sensitive, no questions asked. Okay, there's quite a few things to do then. So hold on a minute, let me think about this. So const trigger is, so let's switch on two things. So that would be so animi dot lint num and animi dot flags dot trigger mode. Right, hold on. Does this actually work? Not sure about the syntax here. The more you know, I guess. So this one here goes away, and we should probably replace this with some sort of yeah. Let's just call this block. And here we are going to do the logic to return that. So if animi dot int number is 1, we return 0. Or rather, we break from the block with 0. Else, if animi dot lint number, or rather, if flags dot trigger mode. So hold on a minute. Here we just we'll need to do this. Here we can just break a block with a switch statement on animi dot flags dot trigger mode. This should be okay. So here we want bus conforming will always go to 0. Level trigger will go to 1, and here I should probably add edge trigger goes to 0 here for this particular case. So this one here would be trigger in value, just so that it's used. Polarity here is also U32, and we create the same block again. Although I'm not sure we need the block here for polarity. Where is, there we go. Polarity of the corresponding pin, active high or active low. Just not sure what bus conforming for this particular case means. I'm just going to go with active high because that's the thing that's most common. So switch on animi.flags dot polarity, and here of course we need to do this. This one here would be bus conforming and active high go to 0, I think. Where was that thing? Active high goes to 0, and of course active low goes to 1. So this one goes like this, polarity. Okay, hold on a minute. This actually sucks a bit. So trigger mode needs to be shifted by 15. I think, yeah, by 15. And input polarity needs to be shifted by 13. So 15 and 13. There we go. Now we just need to set this animi. Animi is 4. So const, what do they call that? Delivery mode. Delivery mode is 4. Of course, this one here is also U32. And this is 4 shifted left by 8. There you go. So this one here, delivery mode. That should be good enough, I think. So the only problem we have here is this guy here. This guy here will cause problems. This guy here is going to cause problems. So I'm just going to do debug. CPU ID is, yeah, okay. Whoops, and then here we go, CPU ID. I'm pretty sure it's not going to pass, or rather, it is going to pass, but it's going to crash here when we try to access FS or GS. It did not. CPU ID, wait, no, that's not it. Oh, we're not calling it. That's that also can help. So CPU here and okay. So what are we doing actually? So hold on a minute. What did we just do? We just went here and called init local interrupts with the local APIC things. Try I guess init local interrupts. And this here would need to be something like this. And we probably need to, yeah, I'm not very happy with this. I'm not very happy with this at all. So here's what we're gonna do. We're gonna make this a public, no, not public, just var, xAPIC, APIC controller, and then we need a type for this. We need a type for this. Are we going to be obliged to create an interface for this? That would suck, actually. That would suck. Okay, you know what? We'll keep it for now. We'll do some other stuff before we get back to that. Right, so this one here we can just remove, probably change with it to do handle local ints for, let's do APIC. And here we can actually go ahead and do init local interrupts. So this here needs smp dot local APIC animi. Oh, and I just noticed something here. This actually needs to be nullable. And this here needs to be I guess options dot max CPU plus 1. Huh. Not sure about the actual syntax, but we move. And now this one here is going to complain that this thing here stopped being that, and this here needs to become this. And now here we need to do if, and probably here we need to do call this maybe animi, sure, if maybe animi, and then we capture animi, and just so that this makes sense, I'm just going to do this. And now we build this and we get all the beautiful errors. You know what? I would argue that a U8 is an exhaustive enum. So I guess that would do the trick. Right, so error union is ignored. Where is that? Hold on a minute. There's no error union there. There we go. Fixed. Now, consider a maiden try. Of course. Okay. Oh. Where does this fail now? Could not allocate output register for constraint. This should be in CPU in this here. So why does it not work? So I don't really need to do this unless I specify the name of a register. So unexpected token in the argument list. Oh, is it because we need to do something like this in AT&T? That's disgusting. And I guess, do we need to put that in there? I'm going to need to take a look at the generated code afterwards. Right, so it was fine before. All we needed is this, I think, and then this. So drum roll. No. What is the problem? Undefined symbol, whatever that is. So maybe just remove that. Okay. Yeah, before we do anything else, I'm just going to need to take a look at opstamp here. But for build kernel elf, yep. And we want to look for GS. We want to look for move GS. Pattern not found. Right, so we want to look for what is our function called ID. That would be CPU.id, maybe. CPU, just CPU, CPU info. Okay, so I'll probably go ahead and just set this to full debug node. All right, let's rebuild this. And here we want X-APIC again. All right, X-APIC init, and we should be just below that. No, maybe. Read register, that's fine. There we go. So enable local APIC. So here we want to where do we get the actual enable, oh, no, that's fine. So enable local APIC is fine. And then we need to go for init local interrupts. There we go. So somewhere here, we are going to need to call into cpu.id. So where is that? So that should be somewhere over here. Yeah, okay. Kind of weird. I'm not seeing the call to ID. I might be blind, but I'm not seeing it. Oh, okay, fine. I'm seeing it now. Right, so let's look for CPU.id then. Okay, so we move GS to EX. All right, that looks pretty okay. Let's run this and see. And of course, we have crashed. We have crashed our operating system because we have tried to read from JS when we haven't said it yet. So yeah, that's actually pretty bad. So things we need to do rather. We need to handle this JS debacle here and point JS into CPU data. There's also another thing we need to do, which would be, so here we have CPU data, which what I'm trying to say is the CPU ID, or rather CPU struct here, CPU data, that contains ARC CPU data is kind of useless because this ID here we have put in this. We basically need to access that from here, from APIC. Except we can do that very cleanly. So we could actually do this GS0 because we know that it's at offset 0. But now that means that we have no way to get the offsets of the other items. So we could have, if we had the type, we could have done something like offset of, and then we pass it the type, the field name, and we have we get, say, computing the offsets for us. But with this one here, we need to be very alert when dealing with the offsets. Otherwise, we might just shoot ourselves in the foot, is what I'm trying to say. Right, so keeping all that in mind, I think this is a good place to stop for now. As always, if you've liked this type of content, hit like, subscribe, all the good stuff. Share the word, maybe tell a friend. And I'll see you next time. Fucking out.